this. Blair Batty is he's your local Tektronix / Keithley guy. So he's up here in Canada. He's kind of trying to come up to speed on some of this. That's why he's here. This is a new role for him. Just like the Tektronix stuff is a new role for me. So we're kind of trying to cross train. So he's just here to observe what's going on here. What I want to do first, I want to ask, what do you guys expect out of this? First of all, this group. Let me know what your roles, responsibilities with this equipment, so I know I can get you the proper training. So fill me in. What do you?
Basically, I am responsible for power system and power electronics lab for undergraduate level, primary responsibility. So this lab is basically Dr. Amin is actually responsible to handle. So he will gonna ask more question.
Okay.
Then if anything comes up or related to power system or power electronics, then I can ask you some question about that.
Okay, so for what I'm interested in, I would like to know all the features of these equipments and how we can use these interfacing with different equipments. I'm not sure, like for example, we have two probe stations. If I am able to communicate between these two through these channels, so that we can transfer informations from one to another through these channels, and also right now we don't have specific questions because we don't know all the features. Probably so when the professors come, they have specific plans and projects in their mind, and we're here so that we know all the general information and we can train up the grad students when they will come to learn. So it's our duty to learn everything, whatever we can cover, and then train up the grad student for their future research.
So if any questions come up during this, just stop me.
Yes,
and
yes.
just feel free to ask questions.
Yes.
Because this is not a typical demo for
Right,
me.
right,
I typically demo the characterization side of it, and from the science standpoint, not so much the hardware. So, but we can talk about all that. So I left it all kind of disassembled the way you got it, so you can see how it goes together. So here's what we've got. We've got a chassis. The chassis it's got a backplane with 9 slots in it that you can option out with different cards. The typical cards would be SMUs. We have 2 different SMUs. You bought 4 of the same, so you've got 4 SMUs. You've got 9 slots. You could put SMUs. You could put pulse cards in there. You could put a scope card. You could put a function generator. You could put an LCR meter. You've got the LCR meter. That's what you see with the gold connectors there. So you've got the LCR meter, and you've got 4 SMUs. There's 2 different SMUs. There's what we call medium power, and there's high power. You've got medium power. I don't know why we don't call it low power. Medium power. But so the specs of the SMUs you have are 200 volts DC max and 100 milliamps max on all 4 channels. Now, you'll also notice one of your SMUs has a preamp, which I've got this connected. So we're going to take that off of there. It has a preamp. Now, the preamp is marked SMU1. That's very important. It only goes to SMU1. You can't put this anywhere else. It's calibrated with that SMU. Okay, there's a preamplifier in here that has to be calibrated with the channel, and the SMUs have to stay in the slot they're in as well. You can't move them around because the different slots in the backplane have different capacitance, so they're calibrated in position. Okay, so I know calibration was one of you guys' concerns.
So if they were to add an SMU or an LCR, they would have to be recalibrated?
Maybe. we have new SMUs that just came out that are field installable that you can purchase. That they're cal to a much tighter standard, so they will work across the whole backplane. They're designed to work in any slot, and basically what they are is they're cherry-picked SMUs that they were able to cal real tightly. So they sell those at a premium. There's a price to pay for them. They're a little more expensive, but you can purchase those. You can plug them in yourself and use them. That's also nice that's nice if you want to add an SMU. You'll never need to add an SMU. You have 4 SMUs. Actually, you have 5. I'll explain that. So you'll never need to add any to this unless you want to go high power, unless you need to go up to an amp. Because the high power SMUs can go to an amp. Now, if you need to calibrate, yeah, it's got to go back to the factory. We can do on-site calibration. You're not going to want to pay for it. It's very expensive. We got to bring somebody out here and all their equipment and stuff. And a lot of people think they can cal these themselves. You're not calibrating nano amp levels occurring here, and it's not going to happen. So Keithley's got state-of-the-art calibration metrology lab. Nobody's going to be able to cal this other than Keithley. So even if you go with a calibration service, they're going to just send it to us anyway. So that would happen in Cleveland, Ohio. There's one good thing, it's not that far from you guys. So these are built, designed, manufactured in Cleveland. So that's one difference between this and all our other Keithley products. Those are all done in China now. These are still done in the U.S. Okay, so your service is local. So what I would suggest is, I saw you've got the boxes over there. Hang on to those boxes, because if you want to send it back for calibration, you'll want to pack it real nicely. And when you send it back, you send everything. Okay, when you send it for calibration, you send everything, because we calibrate to the end of the cable. We calibrate to the end of the cable, which most people don't do. They calibrate to the output of the instrument. We calibrate to the end of the cable. Okay, so
I think we have kind of 1 year for.
we recommend 1 year. When you calibrate, it's really up to you. We recommend a year. A lot of it's going to depend on what type of measurements you're making. If you're making nano-amp, femtoamp measurements regularly, you might want to calibrate as frequently as possible, right? But if you're making microamp measurements, you're going to be fine. For probably a couple of years. But we recommend either way. We recommend 1 year. But ultimately, that's your decision. So,
Okay.
So like I said, we've got 9 slots. You've got 4 SMUs. So in reality, you can do 5 terminal devices, because there's an additional SMU right here in the chassis, which is, we call it the ground unit. It can only source 0 volts. That's all it can do. It can't measure. It can't do anything else. It's just for making a ground. But you're always going to have a ground in your device anyway, right? So you can use that as a 5th channel. So here's the catch. If I were you guys, forget it's even there, because you've got 4 SMUs. An SMU is going to be a better choice for making ground than the ground unit, which sounds weird. But the reason being is that this doesn't have ranges. It's just fixed. And the best way to get a good ground is to switch to the lowest range possible and source 0 volts. Because your error is range dependent. The higher the range, the more error you're going to have on that voltage source. So the SMU has ranges, so you can range it down to the nanovolt range, then source 0 volts. You're going to get a real accurate ground. Okay, this you're not. So that's the difference. If you have an SMU, use it, because it's going to give you a better ground.
Does it operate between rail to rail, or just plus minus kind of voltage? Like
It's bipolar, yes.
Bipolar.
Yes. Yes, plus minus 200. It's actually 205, plus minus 205. So it goes a little higher than 200. Yes. So yeah, it is bipolar. These SMUs are 4-quadrant instruments. Very important to understand. So they can source and they can sync. So what's beautiful about that is now we can test active devices as well as passive devices. You want to test a battery? We can test a battery, a solar cell. It can switch on the fly between sourcing and syncing as well, which is also very nice. It'll automatically just change from a current source to a voltage source, or vice versa, right? So that's really nice to know. It can source and sync the same amount. So you can take 2 channels and just put them together. You won't damage anything. There's no way, because each SMU can sync as much as it can source.
So there is no connection like we have to connect in series or in parallel, so you don't need to think this either matching or resistance matching kind of.
Okay, if you're familiar with this guy, I don't know how familiar you are with this guy. That's an SMU as well, right? That has two SMUs in it. The difference between that and these SMUs is those are floating. These are ground referenced. So that kind of should answer your question right there. You can parallel SMUs for higher current capability. If you were going to do that, I would use that because it's floating. You'd be better off using that. I can go to 1.5 amps anyway. I think is that 2602. So I go to an amp and a half. So yeah, you can parallel and you can series. But in this case, you got to have your ground in the center. You have to go bipolar, right, with the two grounds connected, plus minus, right. You can do it. There's no problem in doing it. But when you parallel, we don't recommend you parallel more than 2 channels, okay? Because now you run into the case where 2 channels can gang up on one, and you can damage the instrument. Right? Now you can source twice the current into one unit that it can handle. Right? In theory, in the factory, we've ganged up 5 of them, no problem, and it works. But we don't recommend it because if something goes haywire, your software or you program it wrong, you can damage things. As long as you're not doing those kind of things, you can't damage this box. It's pretty sturdy. Okay. This is a preamp that goes with channel 1. You bought 1 preamp. You could have had 4 preamps. Don't really need 4 preamps unless you're doing Vanderpool measurements. Then you need 4 preamps. You familiar with Vanderpool? You're not chemists, so you're probably not. Vanderpool is where you're measuring bulk resistivity of material. There's 16 measurements that are needed to do a Vanderpool calculation. And with this system, it'll do it all for you. If you do it, the typical way to do it is to 16 different instrument connections, measurements, and then a bunch of calculations. This is all, it's got it all built in. Because in software, it can walk your current source and your voltmeter around your material without having to lift probes and things like that. Okay, so that's a nice feature. And there's where you only need 4 preamps. But since you've only got 1 preamp, that means only 1 channel will be capable of very high sensitivity current measurements. So that it can measure down in its lowest range will be 10 attoamps, so 10 to the minus 18. And without the preamps, you can measure 10 femtoamps, is what it is, which is still pretty darn low, right? So you just got to know if you got to go below 10 femtoamps, you need to be connected to channel 1 on that pin, because that's where your preamp's going to be. Okay. It's got a PC built in. Is this one Windows 10? No, it should be. It should be, because we just switched over to Windows 10. So this one might be a Windows 10 box. They were all Windows 7. And we're now in the process of going to Windows 10. So this one's probably Windows 10. I haven't even turned it on yet. So it's got a built-in PC. So all your standard Windows account profiles and stuff, that all stands. You can set up accounts so you can have your own account. You can have your own account. You can lock people out of your stuff, by using passwords. And you do that all through Windows. So there's no difference there. So since it's a PC, you're free to load MATLAB onto it, or LabVIEW, or whatever you want to put on it. It's a PC. Antivirus software, treat it like a PC, because that's what it is. We will always have upgrade options for you down the road when Windows 35 comes out. We'll be able to upgrade it to Windows 35. So we may ask you, when that situation arises, which it will, we'll ask you for the serial number of the system, which is back here somewhere. There's a little sticker somewhere down at the bottom. The serial number tells me everything I need to know about the system. I can look it up, and I can tell what version firmware you have in all the cards, and what version firmware you have in the chassis, what Windows you have, what hardware you actually have, because sometimes, depending on the jump, you may have to upgrade hardware as well. Like to go to Windows 7, we had to put a faster processor, more memory, right? So the motherboard changes. The good news is we have always had an upgrade path for these systems. Even if you have one of the first systems that were made back in 2000, they had Windows NT on them or something, we can still upgrade that system to this same level at a very reasonable cost, because we replace everything but the power switch, basically. And we can get you to this level on any system you have, so in the future we'll be able to bring this up to the current level as well. So we're not planning to obsolete it like some of our competitors do, and you just have to throw it away and you have to buy a new one. We have an upgrade path for you. The cards that go in here, nothing's changed on those cards from 2000 until now. The only thing that's changed is the firmware. So even if you got one of those old systems, you can take those cards out, you can plug them in this new chassis with some new firmware, they'll work. Okay.
You mentioned LabVIEW, so it can be controlled also.
Yeah, but once you see the features of this, you'll forget LabVIEW exists. Okay. There's a catch to using LabVIEw. When you use LabVIEw, you lose all the nice fancy features that this box has.
Yeah, well, I
because
guess if you want to automate something or automate something,
you don't need to use LabVIEw, and I'm going to show you why. There's better ways to do it. Some people are just LabVIEw junkies, so they like to use LabVIEw. Knock yourself out. The problem with that is you have to send command lines through LabVIEw. You have to. This has a GPIB controller. I didn't mention. It has a GPIB controller it's set up as a talker. It is your master controller in your system. So this is your talker. So you can put LabVIEw right on here, and then you can use this to control anything else you want to control through this bus. Okay. But if you want to put LabVIEw on an external PC, I got to make this a listener. And there's a way to do that. You can reverse the GPIB port so that this becomes a listener, and you can use LabVIEw to talk to it. But now, your feature set goes away because you got to send command lines. It gives you a command line screen, and when you send commands, they scroll on the screen, so you'll see what you're sending, and what you're receiving off the machine. You send reads and writes to set it up and to get data back. But you lose all the graph. You can put one graph on the screen, I think, is all you can do. A real basic graph, and that's it. So in that case, you'll do everything in LabVIEw. But it's all done for you in here. So that's my point. My point is, using LabVIEw, in my mind, is counterproductive unless you just like LabVIEw so much that you can't stand yourself. You love playing with LabVIEw. I mean, I can't see. You'll see what I'm talking about. The features in here are so nice. They cover. There's a lot of graphing features. There's formulation. You can post-process data after the fact. You can do line fits and regressions and just all kinds of different stuff that you would typically do in LabVIEw. You can do it all right on here, which is really, really kind of nice. So that's why I say LabVIEw. You'll forget LabVIEw exists when you see this. Is my guess. So you can control your probe station through the GPIB. You can do it without any other software application. It can be done right in here. Okay, you can write code that can control any external instrument you want. So I'll talk a little bit about that. So there's you'll need to install a C compiler to do that because we use C. C++. You'll need Visual Studio to do it. There's one catch, and universities typically get Visual Studio for free. You get express versions for free. That won't work because of licensing with Tektronix and Microsoft. They require you have to have a full licensed copy of Visual Studio. That's the only way we can get around that. So you can install it yourself, but it's got to be Pro or Enterprise. It's got to be one of the licensed versions of Visual Studio, and then you can write C code to generate your own GUIs and to control external equipment. Any external equipment you want to control is going to have to be done that way.
So Visual Studio educational version will not work?
Express version will not work. Will not work.
Okay.
Unfortunately. There's another option. We have another software package which for you guys I think is going to be the option because of your semi-automated probe station. We have a software package called EECS. It stands for Automated Characterization
We have
Suite.
professional. So we have professional. Yeah.
Okay.
So
Okay, but since you have an automated probe station, you're going to want ACS. ACS has drivers for that built in, it can do probe moves, and it can do indexing, it can do wafer mapping. It's designed for wafer level characterization. So if you're going to do a lot of indexing and prober moves, ACS is going to be the way you're going to want to go. ACS software, it's basically the same as what's in here, only different. It does a lot of the same things, but it adds the prober control is what it does, and the wafer level reliability tests, and wafer level stuff. It gets added. The ACS software adds some other features that you might like. It allows you to write Python scripts, or C scripts, or TSP scripts. If you're familiar with that guy, you know what TSP scripts are. Nope. TSP is Lua. We call it TSP. It's Lua programming. It's very similar to C++. It's what they use for gaming programming. It's very fast. It's a scripting language. It's non-compiled. And that has an embedded script processor in it that runs Lua. And if you run ACS software, that's what you'll do here. You can write TSP. The TSP commands are Keithley specific. Lua is the compiler we use for it. But we have our own library of commands for all of our instruments. And once you're in that language, now you can control that guy or any other Keithley products that can use TSP can now be programmed in that environment very easily. Okay.
Does it come with EECS, or we should have separately?
ACS is a separate option.
Separate.
Yes. You'd have to buy them. Yeah. And you could load it on here or on a laptop. You can put it on as many machines as you want, but it has a dongle key that you need to be able to actually run tests. So you can use it in your laptops to develop tests and debug and get through the syntax checking, all that. Make sure you can build your libraries, etc. But you can't run it on your laptop. Obviously, you don't have any hardware. But you'll have a USB key that you'll plug into the front of here, which will allow it to run tests on here. Okay. Now ACS can be used on the bench too for instruments like this. You can use it for any Keithley instruments, which is kind of nice. Okay, so talked a little bit about the preamp. The preamp is marked SMU1. Has to go on SMU1. We ship it with it plugged in here. That kind of defeats the purpose of a preamp. The preamp should be remotely mounted. It should be mounted close to your device to minimize cable length, right? So because the A to D hardware is inside of here, so this is where your measurements are actually made. So what we provide you is a extension cable, which it looks just like a VGA cable, and that'll go on here. This will go on the back, and you could put this close to your device. Or, since you bought this option, you could put it in here, which is where we're going to put it. So you're saying, what is that? This is our CV/IV switch. Okay, so what this has is it has 4 inputs for your LCR meter, which you're going to come off of these 4 here with these red cables. Okay, and that's your CV. There's a USB port. This is powered by USB off of here. And then you've got these 4 slots which can accept these preamps, so go inside. Or they can accept these pass-throughs. Since you don't have preamps on all your channels, we use the pass-throughs. These are nothing more than a straight-through connection to bring your SMUs from the back of here to the front of here. Now guess where this goes? Right on your table, your probe station, as close to your probes as possible. Now you'll use 6-inch cables. Or actually you don't need any because you've got little short cables. Which is another thing. I want to commend you guys. This is the first time in years that somebody's done this right. Okay? You ordered a probe station, and one of the questions they ask you when you order a probe station is, how long do you want your cables? And everybody says, give me 2 meters because that'll be more convenient for me, right? You guys didn't do that. You got little short cables. Awesome. Because everything you tack on to this instrument degrades your measurement capability, including your cable length. So keeping those cables short, absolutely key. Because you got capacitance per foot of the cable. It's going to slow down your measurement capability. You're going to have leakage. You have all those things you're going to have to deal with. You guys did it right. The first time in a long time somebody's done it right. So I'm happy to see that. So, but you'll put this on your table there as close to your probes as possible. You've got the little short cables. You'll just run those right to here. And your preamps will be in here. And if you don't have preamps, you'll have the pass-throughs, which will just bring them through here. Now what this gives you the ability to switch between CV and DC-IV measurements without lifting probes. Okay, which the reason that's important is because the cabling is different between IV and CV. This is a triax cable. Does everybody know what a triax cable is? If somebody doesn't say no, I'm walking out because most people don't know what a triax cable is. Okay. Triax cable has 3 conductors. It has a center conductor, it has an inner shield, and it has the outer shell. That's typical of a coax connection, right? So why do I need a triax cable? If you're measuring currents in the 100 nanoamps or above, throw these away. You don't need them, right? But when you start measuring below 100 nanoamps, now there's error sources that can be contributed to the cables that will swamp out your measurements. One of those error sources could be...
How low you can go from nano to pico?
I'm going to add them.
Oh, really?
Yeah.
Okay, that's right.
Yeah. You'll notice this guy doesn't have triax. It's got Phoenix connectors. So you're not going to, even though that's capable of measuring femtoamps, you're not going to measure femtoamps unless you buy, there's an adapter for that adapts from Phoenix to triax. Okay, if you buy, we have another version of this guy, the 2636, which has higher current sensitivity. We don't give you that option. We just put triax on it because you need triax to make very low current measurements. Okay, and a lot of it is because you need the ability to guard, which is a lot of people think guarding is like shielding. It's not. It's guarding and shielding are 2 different things. Okay, this cable has leakage. All cables have leakage, right? So, and it also has capacitance. It also has triboelectric effects. When you do this, you're rubbing the insulator with the conductor, and you're generating voltages, right? All those things matter now when you're in the femtoamp range. They're gonna be significant. But these cables are low noise, so they have very low triboelectric effects. They're very good quality cables. They're low inductance and low capacitance, but they still have leakage. I can get rid of that leakage having that 3rd conductor. Okay, so if you think about it, if I'm sourcing a voltage through the center of this cable, it's going to leak from that center conductor to the inner shield. There's going to be some leakage that it's just going to be part of your measurement. It is what it is. But if I use what's called guarding, which this system is set up for, just by plugging this in, it enables that feature because it senses that you've connected a guard-capable cable. By using guarding now, when I source a voltage to that center conductor, I'm also going to take that voltage, I'm going to turn it around, and I'm going to put it into a unity gain buffer internally in the SMU, and I'm going to drive the guard with that. So what that means is I'm going to have 0 volts across my cable. So what does that do? Shorts out any capacitance, and it eliminates leakage. Because there's leakage is still there, but it's sourced now by the buffer, not by the SMU, so it's not part of your measurement. Okay, so I see the wheels turning. It's a hard concept to understand, but if you see it on paper, you'll get it, and that's the next point I'm going to go to. There's a book you need to. If you don't have it, you need to get it. It's called the Keithley Low-Level Measurements Handbook. Look it up. You'll find it on the web. It's free. There's PDF versions of it all over the web. It's considered an industry standard for this kind of stuff. And what it is it talks about sensitive measurements. We call them low-level measurements. And it tells you about all the error sources you could have with the different styles, different types of measurements you're going to make and how you deal with them. And it talks about all this stuff.
Low level voltage.
It's called the Keithley Low-Level Measurements Handbook. It's a red book. You'll see it. Sometimes we have some copies with us.
If you can provide me your email, I can send it to you.
Yeah.
Yeah, after.
It's a great read. It's not a sales guide. It's an absolutely fantastic read. I've read it like 6 times, and I learn something from it every time I read it. It really is good. It talks about how to make difficult measurements. You know, low resistance, high resistance, low current, low voltage. Low voltage is one of the hardest measurements to make, by the way. There's a lot more error sources, but that'll explain all these things that I'm talking about, and with pictures and nice drawings, and it'll show you. It'll make a lot of sense to you when you see that book. Because these are things that people in the normal engineering world don't even think about, you know, because they're not making sensitive measurements. If you're measuring volts and milliamps, you don't need to know who Keithley is. You know, that's what we do. We make sensitive, low-level measurements. We specialize in it. They're difficult measurements to make, and you have to do it right, or you're not getting good results. So that's for DCIV. We're going to use triads. For CV measurements, coax. Different impedance, different cable altogether. 2-conductor. So now, if you want to make a CV measurement, you're used to probably a typical LCR meter that's got four outputs, outputs, right? Low pot, high pot, low curve, high curve. So you have to bring the 2 cables together, the other 2 cables together. You have to do that, and you got to get those to your probe. You've got a triax probe, so you're going to have to convert from triax to BNC, right? To make that CV connection. What we're going to do is we're going to bring these into the back of here. We're going to bring the SMUs into the triax are going to come in here, coax are going to come in here, and we're just going to have triax on. So now you can go triax to your probes, and you don't have to worry about the difference in the cable. This takes care of it. And this can be switched with software. So I can switch. I could do an IV measurement. Then in software, I could switch to the CV. I can do a CV measurement. You don't have to drop your chuck. So that could be important if you're doing graphene, where contact resistance is so difficult to control. Typically, the contact resistance is 1,000 times higher than the resistance you're trying to measure. So once you make good contact, you want to make all your measurements without moving your probes, right? So that's where this comes in. This allows us to switch between CV and IV measurements. And it does better than that. It allows you to walk your CV meter around your device. If you've got a 4-terminal device, let's say it's an FET, you've got capacitance between each pair of pins around that device. I can walk this CV meter around that device and make all those measurements without having to recable or reprobe. Okay? So it can switch the CV high, the CV low, to any pin, any output. It cannot do that with the DCIV. The DCIV is straight through. But since you got 4 SMUs, we don't have to worry about that, because you've got an SMU on each pin, on each channel. So you can use SMU1, SMU2, SMU3, or SMU4, but you can't put SMU1 up here, SMU2 here. You can't do that. You can do that with the CV. You can't do that with the IV. Okay. Now I discovered a problem when we got here. You've got 2 of these pass-throughs. So these are used in a case where you don't have preamps. See, the preamp's going to go inside SMU1 slot down here. But you don't have preamps for 2, 3, and 4. So you'd use these. Now we got 2. We need 1 more of these. So we're going to have to get you another one of these. So these allow you to bring the triax from the SMUs into this box so that you can get them to the output. We're only going to be able to bring 3 out until we get you another one of these. Jen's going to take care of that, right? Didn't think about that when you guys placed the order. That's my fault. I should have caught that. I did. So what we're going to do first thing is we're going to 3D set this guy up. So I'm going to take this cover off. And we're going to start with the preamp. Now there's this little tab back here. I'm going to pop that off. That's needed if you're going to go to the back here. That screws onto there. Put it on like this. But since we're not going to put it there, I'm going to pop that off. And this is going to slide into, I think SMU1 is the bottom here. So I'm going to take this guy, I'm going to slide it in here. plug in there. Now, these guys, bunch of caps here. Find some we won't need them once we get them all set up. And we'll populate these into 2. It says insert. Once these are in here, you'll never take them out of here. So. We just got to get you a fourth one.
So you should have one more preamp or one more pass-through.
One more pass-through. Unless you want a preamp, we can get you another preamp too. Either one. You need one or the other. Don't really need it, per se. We can go directly off the 4th SMU right to your pro station. So, since being that the SMUs just are pass-through anyway, you probably don't need it. But it's just convenient to have it. Because then you can use, you do all your connections from this. Okay. So now, to connect up the SMU1, we're going to have to use this guy. This little screwdriver came with this, so this is yours. Put this on here. You want to use a flat blade on this one, so it's really difficult. That'll go there. The other end will go to SMU1 because that, like I said, that preamp is calibrated with SMU1. That'll go in here. So that's the only connection you need to make to SMU1 is that these other connections we won't use because we're making all our connections through this cable. Now SMU1's connected. Now to get SMU2, 3, and 4 connected, we're not going to be able to do 4, but we're going to have to use these. Now you'll see this cable's different than this cable. This cable has a triax, 3-lug triax. That's one way you can tell a triax. Look at it, it's got 3 lugs. They used to make a 2-lug triax that looks just like a BNC, but it's not. And it will fit if you force it.
Wow.
And you will damage the connector. So if it doesn't feel like it's going on right, you probably got the wrong connector. But when you don't have a preamp, you have to use these little mini triacs because that's how you get the card's not wide enough for this big connector. So they just use these connectors. Okay, so we'll take this to force. We'll take that guy. This is channel 2 force. We'll go there. And we'll go grab the next one. Okay, so
These are what type of cable did you say? These are coax also?
these are triacs.
Triacs
These
too?
are all triacs.
They're all triacs but different kind?
No, the cable's still triacs. The connector's different.
Okay, okay.
That's all. These are just high density triax connectors, and these are just your standard 3-lug triacs here, which is what you have on your probe station. So
The
this will go-
same as the other cable?
Yes.
Just a different connector?
Yes, a different connector. Correct.
So we connect it from SMU3 or the SMU2?
2. I'm still connecting two. There's two connections.
Connections. Okay.
There's force and there's sense. Okay. Is everybody familiar with what 4-wire measurement is?
Like
We are
differential,
not,
like differential measurement.
No. No. You're familiar with Kelvin measurements?
like a
Kelvin
reed
points.
stone or
You ever done remote sensing on a power supply, where you connect the power leads from a power supply to your device, and then you have to bring sense leads out from the power supply to your device as well, so that the power supply has some analog feedback. So when you tell the power supply set I want 2 volts on my device, there's a drop across the wires, right? But if you put the sense lead, you bring out an extra set of sense leads to the device. Now it's going to feed back what it reads at the device and adjust the power supply. Same thing here. Okay. The reason that works is because if you source and measure on the same pair of wires, you're into a low impedance. The source is a low impedance, so the resistance of those wires is going to matter. It's going to be an IR drop across the cables, right? But now if I separate the source and the force and the sense, we call it. So I'm going to source on 2 wires. I'm going to sense on a different set of wires. Those 2 sense wires go into a high impedance buffer. So therefore your current is 0. So the drop of the cables doesn't matter. Make sense? So that way, when we say I want to force 2 volts to my device, I'm going to get 2 volts. It doesn't matter what the resistance of those wires is. It's going to give me the 2 volts because it's going to sense it wherever your Kelvin point is. The Kelvin point is where you tie the force and the sense together. Now, I haven't done that yet because I'm bringing the force and the sense in separately. They're going to come out of here separately as well. So I haven't tied anything together yet. But now if I bring 2 cables out of here to your device, and then I short them together, now your Kelvin point is at your device. That's what you want. I could short them right here. I put a T on here if I want and bring 1 cable out, but now my Kelvin point's here. And the resistance from here to here matters. Make sense?
And what is the reason that we have preamps for SMU1 and pass through other
Higher sensitivity current measurements.
Also, with that channel we can
Only that. Yeah, if you need to measure attoamps, you'll need to use channel 1. You can measure femtoamps without the preamps.
so they are matched together, calibrated
They're
together.
calibrated as a pair. Not only as a pair, but in the slot that they're in. So you can't move these cards around. Don't even think about it.
So I think the preamp is more expensive than the pass through.
Yes, it's very much so.
So what do you think, like which one we want to first?
Having
Depends on the applications, like if the professor wants to use, more sensitive measurement for different SMUs, then you
Yeah,
can.
you just have, exactly. It's nice if you have on every channel, so you don't have to think about it. You don't have to worry about it. You have the same capability on every channel. Typically, if you're doing FET structures, you'll put that channel on your gate, because that's where you're going to measure the lowest current. Right? Now, we talked a little bit about 2-wire and 4-wire measurements. This system will auto-detect that. That system over there won't. So if you have 4 wires coming off of there, force and sense to your device, and you don't tell it, I want to do a 4-wire measurement, you're not going to get a 4-wire measurement. This has resistance between the sense leads and the high leads, and if it senses a current flowing through there, it knows you've connected those leads, and it will automatically put it in a 4-wire mode, remote sense mode. Okay. So I don't have to use both of these cables. I can just use the force, and that's what I'm going to do for demo purposes here, and I'll show you. You don't need that kind of accuracy. So, but when you connect those sense leads, it automatically knows you've done that, and it improves your accuracy. Okay. So we only have channel 4, so we're not going to do nothing with channel 4. Now, CV. Here's the CV cables. Very important that you use these cables with our CV meter. Our CV meter is optimized for these cables. One of the things being the length. It's an AC measurement, so there's a phase component. So all these cables have to be identical in length and makeup, right? Because if your phase error gets gets off by more than 90 degrees due to different length cables, it will throw off the bridge on the LCR meter, and you'll get all kinds of crazy results. So the length of these cables is programmed into the system. You can change it, but it's defaulted to 1.5 meters, which is what these are.
So you can change the length from the settings.
You can change them, yes. You can compensate. There's what's called compensation. You can compensate for length, you can compensate for shorts, you can compensate for opens, you can compensate for lows. Okay, but, these cables work very well, and we give you this. You use this because that's important. It's a torque wrench. If you don't torque these right, you may not get good measurements at high frequencies. Okay, so, I think these are marked, but no, they're not. They go top to bottom just like they are in the car. And these will go on there. Take care of your cables. These cables are not cheap, and you don't want to kink them. You don't want to, you don't want to damage them.
How
So
much
you
they are?
pull them sideways and put a 90-degree bend right on here, and
How
I'll
much
tell you
these
what
cables
that's
are?
these are rough guys.
US, yeah.
So take care of your cables. Your cables are part of your measurement system, and they're not cheap. These cables are $250 a piece. So they're not cheap cables. Once these are connected, you'll probably never have to move them. So. Okay. That's it. I took off this shield that was on the back. It was there to protect the preamp, but since we're not putting the preamp there, we don't really need it. You could put it there if you want, and then you can strap your cables to it to kind of protect them a little bit, because that's another thing you need to be aware of is that. Cable management is important when you're measuring femtoamps and attoamps. If you've got an air conditioning duct sitting there and it's blowing these cables around like this during your test, guess what you're going to see in your test?
Yeah.
Variation.
Yep. I got a great story about that. I learned my first week on the job. I get called to a university getting noise in their measurement, and they can't figure out why. It's random. It happens for a duration of about 6 seconds, 6 to 10 seconds, just randomly.
Those are the good ones to catch.
Huh?
Those are the nice
those are
ones to
tough
catch.
So I go down to the University of Chicago to try and help them figure out this noise. And they got the system, and it's up against the wall, and there's a hallway on the other side of the wall, and I'm sitting there, and it's not doing it. We got a continuous measurement running, so we can try and figure out what's happening. And all of a sudden, I hear this hum in the back of my head, and I look, and there's the noise on the system. And the hum goes away, the noise goes away. Where the hell's that hum coming from, right? So all day I'm trying to figure out where's this hum coming from. Finally I decide to go see what's on the other side of that wall. I go to the other side of the wall, guess what's on the other side of that wall? A drinking fountain. So every time somebody would come up to take a drink, they would kick on that compressor in that drinking fountain, it would shake the wall. And it was causing the cables to shake. It would pick that up. That's how sensitive it is. So I said, let's move that thing across the room, move it to the other side of the room. We moved to the other side of the room, no more problems. So that's how sensitive this thing can be. You don't want to have any vacuum pumps on your cables, things like that. I've seen that too.
There's some air compressor over there.
Keep that stuff away. Keep it away because it will pick up that.
Not electrical noise, but mechanical.
Oh yeah. Because you're getting triboelectric effects of the cable. You're getting the rubbing of the insulator against the conductor. Whenever these cables move, that's what's happening, right? There's also Seebeck effects that can happen as well, based on the type of materials you use. Typically, they offset, right? You have positive and negative. If you're using the same pair of materials on the high side and the low side, as long as the temperature gradient is the same between those two sides, they will offset. One will be plus, one will be minus. But how often is that the case, where temperature gradient is the same. And the worst is copper oxide. Copper to copper oxide. So if you got oxidized copper, you can get like a volt per degree in offset. Believe it or not. So keep that, all that stuff's a consideration when you're making these kind of measurements. You want to make sure that all your materials are the same. You want to get copper to copper. Because otherwise you're creating batteries. You're creating little batteries in your test circuit. And those are, if you're trying to measure real small things, you just, okay, you gotta move on. Okay, so I'm gonna take these off now, these plugs. These can be used as they're not shorting caps, but they can be used like dust caps. If you want to just see what the ground noise is on the unit, you can put these caps on. You can do a current measurement, it'll tell you what you can get. And for these caps on in this environment, you should be able to see in the hundreds of femtoamps of noise. That's going to be your noise floor. To get lower than that, now you need a Faraday cage, and you need shielding and guarding. So, all the stars have to align. When you want to get below that, you've got to be in the right environment. Okay? The system's capable, but you got to have the right equipment to do it. Darn it. You know what I forgot, right? Squeeze it around this way, no? I forgot to put that back.
Well, we can do that.
We can do that later. Okay. So, we need the, where's the USB cable? Here it is. Okay, so there's USB hookup for this. I'm almost done, because we're not going through all the characterization stuff. We're just talking about the hardware here. This has to go to a USB 3. That's one thing. This needs enough power. It needs a USB 3 port. There's 2 and 3 ports back here. So the blue ones, actually all the ones in the back are USB 3. So plug it in there.
Okay,
Take the power up. Okay, so I think that's all we need to see on the back. Well, any questions on what you see here? I'm going to flip it around now. Yes. Do some cable management. Oh, I just plugged the keyboard in. Plug it in here as well. That's the key in here. Just flip up. And fire it up. Sit down. Cronus. Did you see that? You know what Cronus is? Cronus is a system recovery. If you get so crossed up that you get the system so hosed up you don't know what's going on, you can hit F11 during that power on self test, and it will go to a Cronus menu that allows you to put the system back to the day one status. I've got one in my bag. Now, if you ever have to do that, make sure everybody backs up their projects because they'll be gone. Okay? And I shouldn't have to tell you this, but back up your projects every day. Back them off the system. Okay? Just to be safe, because you're going to have, it's in the university environment, you have all kinds of people on here, so make sure you back stuff up. Now, it complained, and the reason it complained is because this is the first time the system's been set up, and I'm going to show you what we got to do for that. Configuration error has been detected because it doesn't know the configuration as we've got it set up. It has to know the configuration. It has to know what hardware you got. Otherwise, the software doesn't know what's available to it. So we have to tell it to go out there and find all the hardware. So here's our icon. This is a touch screen, by the way, capacitive touch screen. You'll notice there's no optical drives anymore. That was kind of a thing in the past. So now, if you want an optical drive, you're going to have to go get a USB optical drive. Everything comes on USB drives now, but you have USB ports right in the front, so you can log data right to those ports. You can load software through there, whatever. The 5 icons that you get, Clarius is the software that this machine runs to characterize devices. KCON is what we need to run to configure the system. That's Keithley configuration, which we got to do now. KIXI is Keithley Extended Communication Interface. That's if you want to talk to this from another machine, another computer. You have to reverse the system from being a talker to a listener. That's how you do it. You run that. It runs a little application that allows you to send commands to the box and receive commands from it as well. The Learning Center, all your help is there, the manuals, everything's built into this machine. There's also videos. This is an HD box. It has stereo speakers. It can do HD video. The videos you're making, you can put on here. You can make your own videos, put them on here on how to do things. There's a lot of those already here. If you want to know about what guarding is, what shielding is, there's videos on here that show you all that.
Okay.
You can create your own. The message console is for debugging. It puts some of the messages it sends to the message console. It's the only way you can debug it. So first thing we got to do is we got to go to KCON.
Configuration.
So it's only one time.
You have to do it if you make any hardware changes to this box. If you change any cables or you reconfigure anything, you've got to run KCON. Okay? KCON is useful for many things. It tells you the firmware and the serial number. It tells you everything about your system. It tells you what hardware is in the system. It shows you on the left side here what you've got. You can see the SMU1 has a tick, which means it's got a preamp. If I open that, it shows the preamp. See? It shows. Yeah, come on in. So this shows you what hardware I have connected to this machine, and it's software and firmware versions, all that stuff. But what I've got to do is I got to tell it to update the preamp configuration. That's going to go through there, a bunch of clicking and stuff. It's going to go through. It's going to find all this hardware. It's going to create a file, configuration file that the Claria software will use to so it knows what's there. Basically. You just let this run. Make sure you got no devices connected because it might blow it if you do. So you let this run. It takes a couple minutes.
Even when you change the connection from the back, this has to be redone?
Yeah, yes. If you move a preamp or reroute channels or something, yeah, you got to rerun this. If you add a card, add another SMU, you got to rerun this. And things like that.
We didn't make many changes right now. So
No, this is the first time the system's been turned on, so this has got to be done. Well, you will never have to do this again if you don't touch anything. You do it one time.
We are going to get a new pass-through. We have to.
That's just a pass-through, so that won't matter.
Okay.
There's
If you
no
put a preamp, yes.
Yes, because it won't know the preamp's there unless it goes through this process. Yeah, but the pass-through, there's no hardware there. It's just wires that's pass-through. So that won't matter. But, okay, so now this is done. We'll hit save that, and we can get out of here. There's the learning centers here as well. Oh, you're not connected to the network, so that's fine. So you can get out.
So we
you
need
can also network, right?
Oh yeah, it's got an Ethernet port, so you can save your data to the network drive if you want, so you can share things.
So
Can we
Yep.
connect to
Oh yeah, you can
Control.
use remote desktop. It's a PC.
Oh, okay.
It's a PC, so you can use remote desktop.
Can you connect to network to see the learning center? I don't know. Oh no, no need.
There's no need to because it's built in right here.
okay, there's
So here's all your manuals. Here's the user manual, the reference manuals. Oh, I forget it's a touch screen. I hate that.
yes, the mouse.
Oh yeah. Okay.
Yeah, maybe.
Yeah, for demo purposes, the touch screen is a bad idea. So the
Unless you have 5 fingers, I guess.
yeah. So the reference manual is the most important. It's got the most information in it. The reference manual, all your information is in there. There's a video section in here somewhere. Don't worry about that. You'll find it out later. Oh, there's content. That's right. When you get into Clarion specifically. Okay, so I'm gonna get out of here because we can get to that stuff from right here too. There's a learning center. We go right here, and here's all the learning center stuff here. Data sheets, device descriptions, there's videos. So if you want to see, videos, there's videos on all different kind of things. And you can go through all that stuff on your own time. So now KCON is run. So now we can go to Clarius. Clarius is the main software that you're gonna run. And 1.41, the latest. Very nice. So this system has 450 some odd models built into it, test devices. They're already done for you. They're done in two different ways. You have to be able to identify the two different ways. There's what we call interactive tests, and there's what we call user tests. Okay, ITMs, UTMs. ITM stands for interactive test module. UTM stands for user test module. An ITM is just that. It's interactive. We've defined the GUI. We've defined the limits. We've defined the defaults, and you get what you get, and you can use it. You can select from what we've given you, basically. We've decided what you need. Typically, 90% of what you're going to do is going to be through ITMs because they work, they're simple, they're interactive. You don't have to, there's no coding involved. They're just done for you. They're built in. UTMs are when you need something outside the box. When you need something custom, then you generate a UTM. A UTM works through a DLL structure. Are you familiar with DLLs? Where you'll write code and you'll put that code into a DLL library, device link library. And once your test is compiled into the library, now it can be accessed by the Clarius software, just as if it were an interactive test module. But you have to create everything. You have to create the GUI, you have to create the limits and the default settings, and you define what goes on the screen. You define everything. Then it gets compiled into this library. Now you can pull it in. Okay? So that's where the Visual Studio comes in. You need Visual Studio to create UTMs. There's UTMs on here already that are done, compiled in the library. You can use those all day. You don't need Visual Studio to use them because they're already done. But if you want to modify them, you need Visual Studio. Okay? Now, it's set up in three different, there's three different tests. There's what we call select, configure, and analyze. Select is select what you want to test, basically. Analyze, or configure is configure the test, and analyze is analyze the data. So it's a three-step process. So we've got a project here, and this is what you'll typically be working with. You'll work with a project. Now this project has multiple devices in it, as you can see. It doesn't have to be just one kind of device. You can have multiple devices in a project, or you can have a project for one device. And then within that device, you can have multiple different tests. And those tests can even use different hardware. The software will handle all that for you. Okay? And you see the check boxes down the side. So what that means is, if I select this VDS ID that's selected now, and I hit the run button, it'll run that test only. But if I go up one spot to the device itself, and I hit run, it's going to run everything within that device that's got a checkbox. It's going to run them one after another. So you can sequence things together. And that's how you'll do things like with your probe station. You'll add tests in here to move your prober, for instance. And you'll run a test, then you'll index the prober, and you'll run a test, you'll index the prober. And you can put loops in, and you can do all kinds of really cool logic kind of things with the code and your external equipment. Okay? You can control anything that you want externally. Anything that's GPIB. That's how it works. It uses the GPIB to control, to talk to the outside world. Right?
We have one RF probe and one DC probe, so you can communicate with both, right?
Mm-hmm. Yep. They both be connected. Yep. And there's examples on how to do all that on here. I'm not going to go into great detail on that until you're ready to do that. We can help you with that, but I want you guys to feel a little of the pain here. I want you to try some of this stuff, and when you have questions, I'm here to help you. But I don't like to just do stuff for you because then you'll rely on me to do everything for you. You know, and it's not that complicated. You know, there's so many examples on here that most of the time you're going to find exactly what you need already done or very close to what you need already done. And you know, the GPIB stuff is very simple. It's just reads and writes, right? I mean, once you establish a connection to the piece of equipment, it's just IB read, IB write.
So that's the main interface to be used, not through USB or
It's done, everything's done through GPIB.
GPIB?
Yeah, it's all done through GPIB. So it's got to be a GPIB instrument. Now you can use adapters like GPIB to USB. You can do it that way. I've seen people do that. But if you got GPIB, just use GPIB because everything's got GPIB. I'm sure your probe station is GPIB as well. They all have it. Okay, so now this is the system. Now we can select from different tests, different devices, different actions. We have a wafer plan, which would be for your probe station, and then we have projects. So you can create, this is a project, so you can select different projects. You can have a project, you can have a project, you all have your own projects. So you can go select between projects. These are projects that are built in. There's all kinds of stuff. Tests, I mean, there's a lot of stuff here. CV tests, all kinds of stuff. And you can select what you want, and you say add, and it throws it on the left side here in this menu. Devices, if you want to test this particular type of device, they're all here. You can use this on the right-hand side to filter out all of this data, for how many terminals, what type of device, etc. Actions are going to be like you want to beep the beeper, or you want to have a dialog box with a message for your operator, change something, turn on a temperature controller, or whatever. You can put matrices in here, so you can control switch matrices to test many devices in a production type environment. Here's control for the CVIV switch, which is this guy. So that's what an action is. Wafer plan, where you can set up to go to different sites and different subsites, things like that. Program rules, and what projects are. And then configure is where you configure the actual test. So this is a transistor test. What's shown in the center means nothing. It's just a bitmap. What matters is what you do on each individual pin is what matters. I could put a picture of my kids in here. It doesn't matter. So you'll see here where it's got a pull down. It shows me the hardware. All that hardware that's shown comes from KCON that we ran. If you don't run KCON, it's not done right. The hardware won't show up there. So I could put any piece of hardware that's in this box on any pin at any time. And that's how I would do it. I would go here and select that piece of hardware. Okay? And then I can select what I want to do with that hardware. And this is it's a DCSMU, so here's all my options. I can use it as a power supply. I can use it as a current source. I can use it as a voltage source. I can use it as a sweeping instrument. There's a linear sweep, there's logarithmic sweeps, there's a list sweep. A list sweep is very cool. List sweep is where you actually have like an Excel spreadsheet table. It goes right down the list. You tell it my first measurement I want to source 1 volt, next one I want to source minus 5 volts, and then I want to source 3 volts. So you can do arbitrary waveform generation by utilizing that feature. You can even import Excel spreadsheets into that feature as well. So you can do math offline using functions. You can create real nice things that you can pull. And then if you're doing a step, you got to tell it where do I want to start, where do I want to stop, what's my interval, right? So that's what you're doing here. You got to set up compliance. Do we know what compliance is? Yes, no? Okay. Just like on a power supply, you set a limit per se, where you set. If you're sourcing a voltage, you have to set a current compliance, which says don't go above this current.
Limits.
You're telling the source. You're putting a limit on the source to protect your device. You're saying I don't want to ever see more than a tenth of 100 milliamps out of that source. And what it will do is if you're sourcing voltage and you hit that compliance level, it will convert it to a current source, because now it can't source any more voltage because you've hit compliance. So now that instrument turns into a current source until that compliance situation is removed, and then it goes back to being a voltage source. Just like a power supply would do, right? You're familiar with that, right? Okay. So
all these components are coming from that config tool. All the components are hardware that you can choose from the drop-down menu.
What's that?
All the devices and the hardware that you can choose from the drop-down menu is coming from the configuration, what we
Yes.
set up during
Yes.
the configuration.
Yep. Whatever the KCON knows is in this box, will give you access to it here. Okay. This is pretty simple because you really. Wait a minute, I didn't see the CV. Oh yeah, we do have CV. Okay. See, there's the CV meter high and low. So I can put the CV meter in or a DCSMU. That's really what you have, or the ground unit or nothing. That's your options. That's what you have. Okay. Measure current, measure voltage. You have two A to D converters on every channel. So I can source a voltage and I can measure a current and a voltage. So I can read back the voltage I'm sourcing, which is very cool because if you have any loading on your source, you'll see that. Otherwise, you're using the program value, which is not going to be as accurate as the read back value, right? So we're the only ones that do this. All the other people that make these kind of systems, they only have one A to D converter. We have two. So they have to do two sweeps to get voltage and current. We can do it in one sweep, time correlated. So now your voltage and your current are measured at the same time. So that's the other thing. When you trigger this thing, every channel that's configured on here, they all trigger within about 50 nanoseconds of each other. They all trigger at the same time. Okay, so to measure this device, we're gonna step. This kind of shows you exactly what it's doing. It's showing a step function here. It's showing a linear sweep here. It's showing just a DC ground here. And that's just another form of showing the ground. Here I'm using the ground unit, and here I'm just using an SMU sourcing 0 volts. They're both ground, right? So this kind of shows you what it's going to do. So for every step, it's going to sweep the complete sweep range of the drain. Okay, so it's going to set to the first voltage, which is 2 volts. Then it's going to sweep this from 0 to 5. Then it's going to go up 1 volt to 3 volts, and then it's going to sweep again 0 to 5. So what this is going to give me is a family of curves for a transistor, which we should be able to see if I go over here. And there it is. There's your family of curves. Okay, I can hook up a device if you want to see that. I didn't think that was part of the deal with this group, but I can hook up the device. I have a device. We have a fixture here. Maybe that probably should show you just how to hook this stuff up at least, right? Okay, so here's what we got. We got this. This is just a little. This is a demo fixture basically, but you can test devices with it. It's got 2 push pins, so you can put axial leaded devices across here. A little socket you can put transistors into. So we give you some transistors. I'll show you how this works. There's a little shorting wire on the transistors. You have to pull it off, or you will not work. Just to protect the transistor during shipping. I'll throw this guy in here with my old eyes. You can see this.
So this is what, JFT?
It's an N-channel MOSFET. Not BJT. We have BJTs as well. Yeah, my eyes. I think I got it. My eyes just don't work good with these.
Bifocals now.
Did I get that? Okay, so there's my device in there. The fixture's divided into 2 halves: an AC side and a DC side. You're not going to use the AC side. You don't have any AC hardware. There's a pulse instrument that you can get that will do AC. The difference being that what AC is done via coax, not triax, so you have to deal with the shields. The shield is your return, so you have to short the shields together, and you're going to have to do that over there. And I'm telling you this now, but you're still not going to do it because nobody does. You're going to forget about it. When you do CV measurements, it's an AC measurement, so it's basically going through the red coaxial cables where the outer shell is your return. You have to do something with that return. When you're using a two-terminal measurement, AC measurement, you have to tie your 2 shields together. Your probe station doesn't give you the capability to do that. So you have to do it on your own. You have to figure out how to do that. And now this is where you either talk to your probe vendor or you have to make something. And it's as simple as a wire going from the 2 probes to connect those 2 shields together. Okay, so you have your probe, your center conductor for your probe, then there's the outer shield around it. Those need to be tied together. Otherwise you have a big inductive loop that's going to make it very difficult for you to make good capacitance measurements. Okay? And you have to keep that short as possible. You want and as close to your device as possible. So you want to bring your probes in and you want to jumper them right there. You want to jumper them as close to your probe as you can. But we're not going to be doing AC measurements with this. You're going to do AC measurements with that. We can do them here actually. But so these have triaxial connections. So these will go to here. So we just take these additional triax cables, and based on what's set up here, we have to connect the proper channel to the proper pin. So we're saying, what's it? SMU3 is going to our gate. So what we do, we come off of SMU3 force, which is this guy, and we'll go to our gate of our device, which this is marked 8 over there. And we're going from the drain, we're using SMU2. SMU2 force. I'm not going to use the sense lines. I'm just using 2-wire measurements here. And this will go to my drain, which is here. Now, we're not going to use the ground unit, so we're going to get rid of that. We're going to say none. We don't need the bulk to do this measurement. And then for the source, we can use SMU1. Grab another one.
Why is one ground symbol different than the other ground symbol?
Because this is not a ground symbol. This is an SMU sourcing 0 volts. It's a power supply. It's sourcing 0 volts, which is ground. That's the difference.
Okay, but
So it shows it differently.
the sourcing the DC level, but it is set to 0.
Correct.
Okay.
And I just want to show you the difference between the two. And this will go to our source. So there, now we're connected. Our device is connected. Now this test should run. If I go over here, oh no, it won't. It won't. I forgot to explain something. Since we've got this box, you have to configure it. First of all, it's upside down. You can fix that. There. But it's saying that every channel is open. So that means I got nothing connected here. So if I run this test now, nothing's going to happen because we have to set this box up with software. So what we got to do is we got to go to select. We got to go to actions. We got to find a CV configuration, which is this guy. I'm going to add it. I'm going to add it. Well, let's add it wherever it adds it. Add it. We'll add that test. Let's put it in the wrong place, but I can move it. I think.
You can use mouse.
I hate touchscreen. I could slide this guy. Okay, I really want it up here. So before I can do any DC tests, I need to configure the CV-IV box for DC. My options are open, DC, or CV, right? So now what I got to do is I got to go to this test, I go to configure, and now I got to tell it what I want to do on each channel. So I'm going to say, well, 4 we don't have, because we're missing that pass-through, so I'm just going to say open on 4. I'm going to do a 2-wire. Here's where I select 2-wire or 4-wire. I'm only using one cable. It's a 2-wire. And then I can put the names of the pins over here if I want to. So we said channel 1 was the source, so I can come over here and I can say source. I can say channel 2 is the drain. I can say drain. Channel 3 is my gate. 4 is nothing. It's just open. Okay. And now I can run this test and watch what happens to that guy. Run. Oh, fatal come here. What? That's not good. Kite model, fatal come, not acquired K-Sox connection. Never heard of that one.
Something always happens when it comes out.
What are you doing? Just breaking the touch?
Oh, it crashed. This is if your device is light sensitive, you can turn this off because it's going to be sitting right next to your device. And then the light might affect your. That's not. We have to figure that one out. That's probably a firmware thing.
I'm gonna look. It is brand new firmware.
Yeah. That's not good. We'll figure that out. I don't know what the latest firmware is supposed to be in that switch. But we can do that for the next class. We'll figure that out.
That's what happened, remember when we were...
Not that error. That's the first time I've seen that error. I've never seen that before. Let me try it again. Just to be- Oh, it works this time. Okay, so now you see what it did. Now it connected the SMUs from the back to the front, is what it did, except for 4. It didn't do anything with 4, and it labeled them so we know what they're connected to.
So you just reset the software to
I don't know why I
Just
did that.
classic example of just
Yeah.
close it open.
the easiest way to figure out.
Exactly.
Okay, so now I can go to this test, and now I can run this test. If I go to analyze, and run this test, it should run the test. Let's see what happens. Oh, it's running real slow. You know why it's running slow? I'm going to stop it. It's running slow because I've got some voltage turned on. Come back. I don't like this. Oh, it's still working. If you sometimes if you measure current here, it'll be really slow because the current's so small and it takes a long time for small currents to settle. So I gotta turn that off. But for some reason it's not going to. Morning, please be patient. I'm not patient.
I think that's not that big. Current.
Yeah, I know, that's what I'm looking at. That's what I'm a little confused. It's not stopping.
He reset every time that he lose the data, or
That's not good.
it's Core i7 system. That's the configuration.
How patient are we supposed to be here? That's what I said. How patient are we supposed to be? They won't even let me exit. They won't even let me close it out.
Well,
Okay.
I thought that since it's Windows, you can cancel the
Yeah.
task. No?
That's what I was
Oh,
just saying.
yeah.
Control. Yeah.
Yeah, I could have done that, I guess. We'll bring it back. There's obviously a firmware issue going on.
No, no, no.
No system disk. Okay. Let's try this again. Now that's still set up, so I shouldn't have to do anything there. See, and then what I would do is if I want to go from an IV test to a CV test, I'd have to put another one of those configures in before the CV test and change it over to CV, and then reconfigure this and then do the CV. But I don't have to change any probe connections or anything. That's the nice thing. Okay, let's go back here. Configure. Net current report voltage, that should be fine. Net current report voltage, that should be good. Net connected. Bias, this should all be good. There's something going wrong here.
MOSFET is good.
It's not the MOSFET, it's something. I'm not getting any measurements.
The connection is there now.
Yeah.
The software was made a connection. Last time we haven't done this. So you know,
Okay, this is not good, but I think I know what it is.
how it is restarting the software.
Well, there's a trigger controller inside this box that triggers the SMUs. And sometimes during shipping they come unseated. During shipping, the trigger controller. And if I run a UTM, it doesn't use the trigger controller. So if a UTM runs, that tells me that it's the trigger controller. So I can try running a UTM, and we can see if that runs. If that runs, then we can open it up and we can see if we can reseat that card. That's likely. UTMs are triggered via software. ITMs are triggered via the trigger controller hardware.
Internal triggers and
Yeah, those are the software triggers. So I can come back to there. I love demos.
Keeps you on your toes.
Murphy's law.
Yeah. We'd be opening this up.
Do you have what you need to open it up and see it?
Yeah, I may or may not be able to fix it though.
Yeah, we can get the hunt tools if you then right? I don't know if you guys want hunt tools, but you can hunt tools.
I should have everything I need.
We don't recommend you open it.
Yeah, I
Yeah.
don't think you need that.
Only Mark.
It's a software issue.
No, it's a hardware issue. That's what I think.
Sometimes they become loose inside.
Yeah, we're bouncing around in a truck. You know, it can happen. Okay, so what we need to do is we need to find an ITS or UTS. You can tell the difference by this is an ITM. Projects. This I know is not. This is got UTMs in it. This is for the pulsar. This we have. We have any UTMs that work just for SMUs? I don't even know. Let's see.
So every time we do this is a new project.
This should have. This should be a UTM. don't think there's any UTMs for this SMUs though. They're so simple. I don't think it has them.
Can you make one? Oh, no, we need it.
I need some data. I need to see that I can get data. Solar stuff. Or we just open it up.
Well, that's something for us to learn, just in case.
There we go. You can tell this is a UTM because it asks for a library and a module. So here's their list of libraries. Here's the modules within that library, only one. So here's the yeah, see that runs. Trigger can go in. So we're gonna open it up.
So this is the ITM running.
This is a UTM. It's a UTM. So this is software. This is C code that's running. So the triggering is all done in the code. So that's why I'm suspecting the hardware. Because the ITM uses hardware triggers. Okay. So let's open it up. You guys are probably more interested in that anyway, right?